Good day, everyone. Welcome again to the MathCAD tutorial sessions. Today we're going to go over lesson number 3, which includes data analysis, some statistical analysis, as well as programming and the function blocks and programming blocks. And so let's start with the lesson today, and let's go to the next slide. Now, MathCAD provides the ability, as we saw on the last lesson, of embedded functions or built-in functions. Some of these functions are with the purpose of performing statistical analysis, and it's very important when it comes to gathering data from experiments or gathering data from problem solving. MathCAD offers the capability of performing statistical analysis by a number of built-in functions that can be applied directly to data contained in single or multidimensional arrays. For example, the three basic statistical functions, the mean value or average, standard deviation, and variance, you can calculate directly using these functions. So let's go straight into MathCAD and let's just put this concepts in practice. I've included some files in MathCAD, and on the MathCAD 03, which is lesson number 3, I've included a MathCAD-03.mcd, which can be found in the same location where this presentation is. And by opening that presentation, what you get is a template or a pre-filled MathCAD spreadsheet with several exercises. Let's go over them. So for example, if you're given a vector A, which is a one-dimensional or a column vector, with some data, that data, let's say, was collected from some experiment, or it shows temperatures of a particular phenomena or a particular measurement, but we have to perform some statistical analysis over this data. We know that the formula for average is, well, we have a vector with 11 quantities. If we add them up and divide by 11 the number of quantities, we should get the average value. But we don't actually have to write this formula. This formula can be written using the summation sign and dividing by and so on. We can just simply say mean of A, and in parentheses the value of the array or the name of the array, and we get exactly the same number. We can also calculate the standard deviation, STDV of A, STDEV, 25,421, which the standard deviation is simply the average difference or the average deviation between every single data and the mean value. It gives you a an illustration of how spread out the data is. And the variance of this data, 646.248, which is simply the square of the standard deviation. Okay, that's how the variance is defined. So let's go back to the presentation. Other functions, other interpolation functions or statistical functions include MathCAD is capable of automatically performing interpolation using several order of approximations. First one, you can perform linear interpolation, which is nothing but just linear fits between points in the data. Linear splines to connect data with line segments. Polynomial splines or parabolic spline, PS spline. Cubic spline, which is the most commonly used form of splines. And general interpolation, interp, and correlation to actually determine the quality of a particular interpolation. And we'll talk, actually we'll clarify some of these concepts directly on the MathCAD spreadsheet. So let's say on the second part of this exercise, you are given a vector with time and a vector with temperatures. So these are temperature measurements of a particular event that occurs in time from 0 to 1. That can be days or it can be hours. Every 0.1 of an hour a measurement was taken, and this is how the temperature rises, or as you can see. And this data, obviously, since it was taken through a specific measurement type, through a thermometer or infrared thermography or whatever it was, it includes some random error, it includes some measurement error. What we want to do is try to find out if there is a specific behavior to this particular phenomena. We can see that the temperature rises, but how does it rise? Does it rise as a line? Does it rise as a parabola? Does it rise as an exponential function? Does it rise like a segment? What does this line follow? And for that, we try to perform curve fit or back interpolation to see what is the best interpretation. The first thing we can do is perform a linear interpolation, lin interp actually linterp of time t, the two vectors, the vector time, the vector t, at a particular time. Let's say I want to interpolate this data. I know what the data looks like, and I know the discrete values of temperature at a specific discrete values of time. But if I say, well, I want to know what the value of temperature is exactly at 0.75, and between these two, what MathCAD will do is perform a linear interpolation between this value and this value, and this value and this value will give you 219.5. That is not necessarily the best interpolation, but it's an interpolation. Okay. What linear interpolation means is that, well, you're actually taking an average of the values of temperature in between each 2 points. So you're actually drawing line segments between the points and looking at the value interpolated in between, just by looking at the two consecutive points, the two neighboring points. So if I want to know the value of 0.75, which is somewhere around here, I want to know the value of the temperature, I know it has to be somewhere in between these two values. A line is drawn in between these 2 points, and the interpolation value is gathered using this function. I can also perform a spline interpolation, and the most common and useful form of spline is the cubic spline, which actually connects every single point using a cubic polynomial, and it actually connects the curves or the cubic polynomials using some continuity and smoothness criteria. So all the cubic polynomials are connected. The slopes of the cubic polynomials at the intersection are connected, are the same, and the second derivative or curvatures of every single one of these cubic polynomials are the same at the connecting dots. So I can find the coefficients of this cubic interpolation, C spline, cubic spline, time, and t. So this particular operation, C spline, gives me the coefficients of that cubic interpolation operation on these functions. And then I can interpolate the data using these coefficients BC, the time, the temperatures, and the value of 0.75. Now, what is the value of temperature at 0.75 hours? If I do it through linear interpolation, I got 219.5. If I do it using cubic spline, which should be a better interpolation, I get 219.492. You can actually trust that this particular one is a better interpretation or a better interpolation of these temperatures at that point, because it used curves instead of straight lines, and in this case we use cubic polynomials into or within each of the points. Okay, so going back to the presentation, we already looked at what is cubic spline, what is linear interpolation, and the interpolation, general interpolation function. Now this correlation function actually correlates two vectors and see how similar they are to each other. If they're exactly the same, the correlation is 1. So there's 0 residuals between the two vectors. If these two vectors are identical, the correlation between them is 1. The farther you are from 1, the worse the correlation is. So you can tell if you're actually performing some sort of curve fit of the data, what kind of interpolation or what kind of curve fit gave you a better correlation. And we're going to exercise that later. Other functions for curve fitting can be the intercept and the slope, which will actually find, if you give a set of data points, it would assume those points correspond to a straight line. It will find you the intersection with the y-axis and the slope of that line. And then you can linear fit that curve. You can use linfit to plug those values into or apply a generalized regression with a function f, which we'll be exercising next. Let's go back to the presentation. Now what we want to do is, given this data, time and t, let's do a linear regression. Let's presume that this data belongs to a straight line. Okay? That the general behavior, the general mathematical behavior behind this temperature increase is a straight line. It doesn't look like a straight line, but I'm going to make the assumption that this is a straight line. I'm not talking about segments in between points. I'm talking about linear regression, linear curve fit. So there's got to be a line somewhere with a specific slope and a specific y-intercept that would actually fit through this data. Let's find what the equation of that line is. Now for that, we're going to use the intercept and the slope. We're going to call the intercept B, intercept of time and t. and that b is equal to 193.909. So if there is an equation of a straight line that goes through this data, that fits through this data, that line is going to intersect the y-axis or the t-axis at 193.909. And then the slope, m, we're going to call m, slope between time and temperature, m. Now notice that I've already created a vector here on the template file that has 11 points between 0 and 10, and those points are going to be interpolating the data given by this slope m and this y-intercept b. So the linear interpolation or the linear curve fit of this data is going to take the form of a linear function with slope m and intersection b. Okay, and that blue dashed line is exactly the function of the straight line that actually passes or the best fit this particular data that was given to us. Now obviously, as you can see, a line doesn't really do a really good job of capturing the behavior of that data. This looks more like a parabola or a space of a parabola, or even more like an exponential function, which is usually what temperature distributions follow, some sort of an exponential function. So we can correlate the two data. We can correlate the given t and t dot linear, which is the interpolation that we just made, and compare. Notice that the correlation is 0.954. It is actually far from 1. 1 is a perfect correlation. 0.954 is not a bad correlation, but it's a correlation that gives you an average about a 5% error in the data, or to the data. Now the second type of interpolation that we're going to use is the linear fit. And in this case, we can come up with any type of function we want. In this case, we're fitting, for example, a parabola, because we're using three different functions. The three functions that compose a parabola are 1, x, and x squared. The general function for a parabola is a plus bx plus cx squared. So we're going to pick these three functions. We can pick as many functions as we want. We can pick even a cubic polynomial, x cubed, fourth order polynomial. But in this case, we're going to define function x as a vector of 3 rows and 1 column that contain 1, x, and x squared. And then we're going to perform an interpolation. The coefficients of that interpolation are going to be a linear fit. We're doing a curve fit given time, given the temperature, and given this function that we define in here. And if we show what a are the coefficients of that parabola. A, b, and c. A times bx times cx squared. If we put that into a parabolic spline or a parabolic curve fit, notice that the data is actually interpolated a lot better. And what we're doing is just creating a vector with 11 entries from 0 to 10 that interpolates the data of time using the coefficients a0, a1, and a2 that we just found here in this particular interpolation. And if we correlate now t and t parabolic, we'll find for sure a better interpolation. Notice that this was the linear curve fit had a correlation of 0.954. The parabolic curve fit has a correlation of 0.998. So less than 0.2% in average residual between the two functions. The numbers that were given to me, or the data points that were given to me, and the correlation. So it looks like we did a much better job of fitting this data using a parabola than using a linear function, obviously. The parabola looks much better through the data. Can there be any better? Well, I said that if you know the physics behind temperature distribution and temperature raises, there seems to always be some sort of an exponential function behind it. So let's try to perform an exponential type of curve fit and see if we find a better correlation. Let's go back to the presentation. There's all kinds of different regressions. These are nonlinear regressions because we're going to be finding coefficients that are not linearly related to basis functions. So there's an exponential fit, which is the one that we're going to try. So in an exponential fit, you give the vector that corresponds to the x-axis, this is the time, the vector that corresponds to the y-axis, this is the temperature, and some guess values of the coefficients. You need to guess what A, B, and C are going to be. There's a logarithmic fit, and you also have to give guesses, A, B, and C. There is a log fit. I'm sorry, this is a rational function, irrational function fit, irrational exponential. This is a log fit. This is a power fit, and this is a sine fit, sine function with a phase angle and an amplitude and so on. So let's see. We're going to use an exponential fit and see how well we can actually correlate this data. Let's give some guesses again for A, B, and C. I'm going to give guesses of 1, 1, and 200 for A, B, and C. Remember that A, B, and C are the coefficients A times e to the bx plus c. So we're going to be finding E, B, and C to correlate that data time to temperature. And then we're going to say A is an exponential fit. The coefficients A are an exponential fit of time, temperature, the two vectors that were given, and BG, which is that guess value of coefficients. A came out as 4.338, the value of A, that's this value. The value of B came out at 2.295, that is the value containing B, containing X on the exponential, and the intercept C is 194.622. Now notice that if I change the initial guesses, these values might change because it's a nonlinear interpolation, so there's not a unique solution for this interpolation. There are many possible solutions for this interpolation. If I change this value to, let's say, -1, I might find another interpolation, but it all depends. If I change this to 100, it didn't even find a solution. If I change this to 20, I found virtually the same solution, but just leave it. Let's just leave it at those initial guesses, and then let's fit that data into another vector called texp, which has A, B, and C. A is A0, B is A1, 2.295, and C is A2, 194.622. E to the B times time correlates the data just like this. And if we want to see analytically what is the correlation between the data that was given, T, and the exponential curve fit, we get 0.999, so less than a 0.1% error in between the correlation and the exponential function through the curve fit and the data that was given. Now notice that this is better than the parabolic interpolation, and it just happens to be better because this data somehow comes from a exponential function. So as I said, you can perform all kinds of different interpolations. You can perform the inverse exponential function, the logarithmic function, logarithmic curve fit, power fit, and sine fit. And remember, VG is a set of is an array with 3 values, which are the guess or initial guesses for this nonlinear correlation, or this nonlinear curve fit. Now, this is data analysis and the use of statistical functions to perform analysis on provided data. As we said, we perform analysis of standard canonical statistical values like mean values, standard deviation, variances. We looked at interpolation, linear interpolation, splines, linear splines, parabolic splines, cubic splines, and we looked at then general curve fit, linear curve fit or regression. Then we looked at general linear regression, where we perform a parabolic as an example. Then nonlinear curve fit, which included exponential, logarithmic, sine, and so on. You can actually come up with your own type of curve fit or interpolation, and if you know what the behavior of the data is a priori, if you know what the function should look like, and then all you want to do is determine the coefficients of that function, you can use some of these functions, MathCAD embedded functions. So the next study that we are going to perform in the next set of slides is the use of function blocks and programming blocks to perform MathCAD programming. So not only MathCAD serves as a mathematical spreadsheet with what you see is what you get capabilities, where you just pose the problem, type in the data, and get the results, and do this in a parametric fashion. You can also actually write programming blocks and perform iterative type of operations and perform conditional type of operations. You can do so using the programming toolbar. The programming toolbar just contains 10 simple statements. At line, assignment, which is the same thing as equal, but in a programming block. In a programming block, you don't use the definition equal or the assignment equal. You actually use this type of assignment. If you're going to use a comparing equal, you use the control equal, and we'll look into that. You have the conditional if, the opposite of the conditional otherwise, for looping, while for looping with a condition, break to get out of a loop, continue to continue within a loop, return to exit the programming block, and OnError to actually catch errors in the programming block. So let's start by using some of these statements in the programming toolbar. The add line, for example, and let's program a function called the thermostat. A thermostat is a function that would probably require some conditioning. It will probably require some questioning, because it is not a function in the sense of an algebraic function where the thermostat t depends on a single algebraic function of t. Okay, it's not a times t to the power of b or anything like that. It is a discrete function that depends on t. Well, a thermostat works. Let's say that we're programming a three-way thermostat, not a single two-way thermostat, a three-way thermostat that is open if the temperature is between a range or is within a range, is closed if the temperature is within another range, and it is open to another gate if the temperature is within another range. So let's program a thermostat that gives you a value of -1. Let's say a -1 will send a signal to the system to turn on the heater. Okay, -1 turns on the heater. A -1 if the temperature is below, let's say, 60 degrees. If the temperature is between 60 and 70, let's say it provides a 0. And a 0 is for not turning the either the heater or the air conditioning. And if the temperature is above 70, then turn on the heater or turn on the air conditioning. So how do we do that? We do that with programming blocks. Let's go back to the presentation, and the first thing we're going to do after the page break is open the programming toolbar. This is a programming toolbar. We can find it on the general toolbar or just by view toolbars, programming toolbar. And let's also open the Boolean toolbar, because here in the Boolean toolbar we're going to have access to some arithmetic tools, like the Boolean comparison tools, equal to, less than, greater than, less than equal to, greater equal than, that we are going to use when conditioning these programming blocks. So we're going to program a function called thermostat, and that thermostat depends on a temperature. And as I said, this is a three-way thermostat, so we'll provide either three signals to our HVAC system. The signal is either -1 to turn on the heater, 0 to turn everything off, or 1 to turn on the air conditioning, see, or the cooler. This function is going to be equal to, notice that I use the definition equal, and I add a line. That adding a line opens a programming block. Okay, so the first thing I want to say is that a is less than, and a is a general variable that I use within my programming block. It's just local to the programming block. It doesn't have any meaning or value outside the programming block. I'm just using it inside. And notice that I am defining a, local definition, a. I don't use equal. It doesn't even come up when I try to press equal. It's defined as -1, and I select the whole thing, if a condition, if the temperature is less than, or I can pick the less than, let's say 60 degrees. If the temperature is less than 60 degrees, send a signal to -1 to the system that will turn on the heater. On the second line, I'm going to say a is equal to 0 if, do not write, by the way, do not write if, because that's not going to, MathCAD is not going to understand it. You have to click on the if. There's a shortcut for every one of these instructions, every one of these programming instructions. So if the temperature is greater or equal than 60, and, which is this particular arithmetic operator here, and T is less or equal than 70, so if the temperature is somewhere between 60 and 70, send a signal of 0. The third line, add a line, A is going to be equal to 1 if the temperature is greater than 70. Now we cover all the ranges of temperature. Somewhere between 60 and 70, the system is going to be off. If the temperature of the room is below 60, I'm going to turn on the heater. If the temperature is above 70, then I'm going to turn on the air conditioning. And the final statement of each programming block is usually a return. I want to return the value of A to correspond to the value of this function thermostat. Okay, so the thermostat function is going to take on the value of either -1, 0, or 1, depending on the value of the temperature. So let's test that. Thermostat, and let's say if the temperature of the room is 50 degrees, then there should be a signal to turn on a heater. That's the -1. -1. If the temperature is, let's say, 65, nothing should be turned on. That's 0. And if the temperature is 75, a 1 should be sent, a signal of 1 should be sent to turn on the AC. That's how you electronically program these controllers or the thermostat. Okay, so let's continue with the presentation. So in this particular example, we looked at the at line statement, which the short would notice that in the triangular brackets I'm given the shortcut is a right square bracket. Local definition, that's the left pointing arrow. We looked at the if, the conditional, and notice that the example that I'm giving here is slightly different. I'm using a different range of temperatures. I'm giving a default value for A. And in the conditional if, notice that the definition of a conditional statement is simply it performs the operation, which in this case is, for example, A is set to 1 if the temperature is less than 60. Very easy to read. And then the return statement, which should always, or very commonly, be the last statement in a programming block, because it's the one that returns the value, the local defined value. A, remember, is a local variable that only has meaning within the programming block. We don't have access to A from outside, from the outside world, from the outside of this programming block, but we return it as the value of thermostat once the programming block is over. Okay, now let's look at another type of statement, which is the otherwise. The otherwise actually gives you the opposite of the truth condition and the conditional statement. And let's look at this particular example, the field valve. Let's say that we have to program also a discrete type of programming, a field valve. Okay, it's a function, but it's a function that doesn't follow a smooth transition like these functions that we define above. It's not an exponential function. It's just a function that takes on a couple values, like this thermostat takes only -1, 0, and 1. The field valve is only going to take, in this case, open or close. Okay, so not only this one is a discrete type of function, it doesn't even return numerical values, it returns strings. So the field valve depends on a level. Okay, depending on the level of a tank, this valve is going to send a signal to the pump to tell it to, or to the gate, to the solenoid valve, to either open it or close it. Now if the level is above, let's say 5, we open the valve, and if the level is if it's below 5, we open the valve. If it's above 5, then we close the valve. So how do we do that? This is a simple two-way conditioning. So that's a very common situation in which you will use the otherwise. So we're going to say A, which is a local scope variable again, and we're going to set it up to, in quotes, open if the level is less than 5. If the level is less than 5, then open the valve to fill up the tank. Then A is set up as close. We could say if the level is greater or equal than 5, but we can just say otherwise. It will be identical. So these particular statement will be the same thing, as saying if level is greater or equal than 5. That's exactly the same, but I don't want to do it that way. I want to do it with the otherwise, just to exercise or to illustrate the use of this particular function or statement. And then we add a line, because the last line of a programming block is usually a return. And what are we going to return? The value of a, the value of this local variable a, to take on the value of this function fill valve. So the function fill valve depends on a level. If the level is 3, the valve will be open. If the level is 4, the valve will be open. If the level is 6, the valve will be closed. So as you can see, it's a two-way function that can only be done in this case through some conditioning, some programming. Okay. So another very powerful ability of this programming block is the ability of performing loops. Okay, and that's a feature that every single programming language, or in this case a programming block type algorithm, should contain. You should have the ability of performing loops. In this case, the for loop is a non-conditional loop. It is conditioned to the range that you provide in the statement of the loop. Let's say that we want to program a function called summation that will take a single input n, and it will simply sum all the numbers between 1 and that value n. So if I say summation 100, it will add up all the values 1, 2, 3 all the way to 100, add them together and give you the result. We can do that with a simple formula, or we can do this for illustration with a summation programming block. Okay, so let's try that. Summation of the first n numbers. Add a line. Let's just initialize this internal value. I usually use a. You can use whatever you want for the name of this internal variable. You can use s. And then we set up a for loop, and we're going to loop the variable n. Notice that it's not the same as capital N. I can use I if you want to. We can use n to distinguish from 1 all the way to this provided value of n. Okay, so we're going to loop. We're going to execute this line of code. This is a line of code that belongs to the for loop, which we can actually add. So we created a sub-level of programming statements that belong to the for loop, but we are not going to need that. We're probably going to need only one. That will be a is equal to a, the current value of a, plus n. So that is actually adding all the values. 1, notice that lowercase n loops from 1 to n, whatever n is. If n is 100, it will take on the value of 1, 2, 3, all the way to 100. And then we're adding all those values together into an internal variable a. And then at the end of this process, we add a line and return a. So let's say, what is the summation of the first 20 numbers? 210. What is the summation of the first 100 numbers? Okay, let's just modify this result. And let's just put in this exponential threshold at 6, so we see the entire range of that integer number. What is the summation of the first 500 numbers? 125,250, and so on and so forth. So we can add as many numbers as we want using this formula. Notice that there's a Gauss formula for adding the first n numbers, and that is sum of n is equal to n plus or times n plus 1 divided by 2. So I can do exactly the same. Sum of the first 500 numbers is equal to, and let's just format this result with an exponential threshold of 6, and I get exactly the same result. So a simple formula would actually take the place of this programming block, but it's because a formula exists and we know about this formula, but otherwise this is a good illustration of what the for loop does. Alright, let's go back to the presentation. Let's look at the while. The while is a conditional loop execution. It will execute the statements that belong to the loop until a condition is not met, or it will execute it while the condition is met, while the condition is actually true. So let's actually write the same summation programming block, but instead of using a for loop, let's use a while loop. It requires just one more line of code. We define A as 0, we start N as 0 too, that's the counter. We add a line, and now we're going to use a while instead of a for loop. The while is just going to say, well, N is less than N. That's a big N. We're only going to increase the value of N. N is equal to N plus 1. The same thing that the for loop is doing is looping N from 1 to N in steps of 1, 1, 2, 3. The same thing we're doing here. We're starting N at 0, and then we're adding 1 to that value. So the next value is 1, the next value is 2, the following value is 3, and so on. What else do we do? Add a line within the while loop and say A is equal to A plus N. So we are going to add up all of these values from 1 to N. Same way we did it before, but now we're doing it with a while loop. Notice the difference between return A. Notice the difference between the while loop and the for loop. Okay? The for loop actually explicitly states the range of the variable to be looped. In this case, N is looped between 1 and N in steps of 1. In the while loop, all we do is state a condition. Do this while this condition is true. So we can use the while loop in a wider variety of programming situations than we can use the for loop on. Okay? Actually, you'll get more and more familiar with these concepts when you go through programming classes, when you go through computer programming classes, or you actually take numerical methods, whether you're in computer engineering, electrical engineering, mechanical, civil. You're always going to be exposed to these type of numerical techniques. And we're also going to cover MATLAB, and in MATLAB you're going to be exposed also to these programming techniques. Now notice that the summation is underlined. That means that we are actually overloading this function. We are recreating or rewriting on top of this function. MathCAD is giving us a warning because we already defined a function called summation. We're defining it again. So let's say summation of the first 500 numbers is equal to, again, we don't want this in an exponential format, so we want to increase the threshold. It is exactly 125,250, which is the same thing we found before. Okay. Now let's see what else on the presentation. The break. The break command is used to actually get out of a loop. Whether you're in a for loop or in a while loop, it would actually get out when the condition on the break is true. So you say break if, in this case, let's say that we want to program the summation block either with a while or with a for. It doesn't make a difference, but we want to make sure that we only add up the first 100 numbers, and then we don't do anything after that. So if the number you put in parentheses is larger than 100, it doesn't make a difference. Only sum the first 100 numbers. So let's see. How do we do that? Let's just take this block and make a little change to it. It's a summation n, but this is a summation n that is truncated at 100. This particular function, for some reason, this is just an illustration example, it would only give us the first 100, or the summation of the first 100 numbers. And in order to do that, within the while execution, notice that the while loop is performing these two functions while this condition is true. I'm going to add a line and say break if n is greater than 99. So n, which is the looping variable, is going from 1 to n, is going to stop at 99. So if I say that summation of the first 50 numbers, and let's just again change this notation to change the exponential threshold. The first 50 numbers is 1,275. The first 90 numbers, 4,000. The first 99 numbers, 4,950. The first 100 numbers, 5,050. But after that, it will give me the same 5,050. It will not give me the value of the summation of the first 150 numbers. It will only give me the value of the summation of the first 100 numbers, and that's it. It will stop there. So it doesn't matter what number I put in here, it will give me the summation of the first 100 because of this break function right here, or the break statement. Alright. Now another very similar statement is a continuous statement would actually do the opposite of the break. Is also used in loop executions within the loop. In this case, I'm using it within a for loop to block parts of the loop depending on a condition. So in this case, notice that we're doing a double summation of two numbers, n and m. Okay, so it should provide a double summation of n and m. It should actually give us back the multiplication of n times m. Now we're adding a little condition that says continue if n is greater than 100. So it will give me the multiplication of n times m all the way up to n equal to 100. If n is greater than 100, it will stop at 100. Okay, so we do that with a continue. This is another maybe useless type of function. We cannot see the connection here. We cannot see the application right away, but it's just the illustration of the use of this particular continue statement. So let's program the double summation, and this double summation takes on two parameters, or two input variables, n and m. And what this one's going to do is, let's just initialize a as 0, then for loop for n, lowercase n, that loops through the range of 1 through n in steps of 1, capital N, and we're going to continue if n is greater than 100. So we're going to only do this for the first 100 values of n. Okay, and then we're going to do a second loop for, oops, we're going to first of all add a line here, and then a second loop. Within the n loop, we're going to do an m loop, and the m loop is going to loop from 1 to capital M, and then a is going to take on the value of a plus 1. Okay, so you're simply trying to multiply n times m. It should be called a double multiplication, or the multiplication of n times n. It's a truncated multiplication. So we're actually trying to multiply n times m, but when n is equal or greater than 100, it will stop right there. And let's just try to see this as an illustration. Add a line and return a. Let's see this with an example. A double summation of, let's say, 50, 60 is equal to 3,000. Let's just change the way we see this result. Increase the exponential threshold. 3,000. 80 times 60, 4,800. 100 times 60, 6,000. But if I make this number 120, I still get 6,000. If I make it 150, I still get 6,000, because it stops at n equal to 100 because of that continue statement. Blocks the execution of that loop if n is greater than 100. Okay? So it's very similar to the break statement. You can actually do with one what you can do with the other by programming it a little bit differently. Alright, so let's go back to the presentation. And the last statement on this programming toolbar is the OnError. The OnError statement is actually used for programming validation, to actually trap errors. Okay, let's say, for example, let's say that we're using, or we want to program a function called inverse of x, which is 1 over x. Okay, that's the inverse of x. Nothing wrong with that. Inverse of 10 should be 0.1. Okay, perfect. How about the inverse of 0? it gives me infinity, it gives me an error. I don't want that error to occur. I don't want this problem to break down if I'm going to use this function later on a bigger problem. I don't want this function to break down and give me a runtime error and stop the execution of the entire code if I get a parameter of 0. So what I'm going to do is I'm going to create a function called inverse that is defined a little bit differently than this, and it's done through a programming block. Okay, and the function is going to be, let's start by simply initializing an internal variable, and then we're going to use an OnError. We're going to say a is equal to infinity. Okay, OnError, a is equal to infinity. If this provides an error, if this particular function provides an error, a is equal to 1 over x. If this particular statement provides an error, then retrieve back to this validation and say, well, the value of a is infinity, and then return a. So now I can say, what is the inverse of 10? I still get 0.1, no problem, but if I say, what is the inverse of 0, I get infinity, because I trapped that error using the OnError statement inside the programming block. A very useful routine when you need to use, or a very useful statement when you need to use this particular function and some other functions, and you don't want the whole process to break down. Okay, now another use of programming blocks is to actually merge functions. If you have a function, that we've done that with discrete functions like the thermostat, the field valve, and so on. But let's say that you have two mathematical functions that are connected together, and you want to express this function as a single one, because you need to integrate it, because you need to do something to this function. So you need a single function f of x. Okay, and that function is not a parabola, it's not a line, but it's a combination of the two that connect at a particular point. Okay, so you do that through a programming block. For example, if the function is a line when x is less than 0, and it's a parabola when x is greater than 0. So how do you do that? Let's go back and say f of x at a line, z or a, whatever you want to call it, let's say a to be consistent with what we have been doing, is equal to 0. So we say a is equal to minus x. It's the equation of a straight line pointing down. That's if x is less than 0. Add a line. A is equal to x squared if x is greater or equal than 0. And now add a line and return a. Now let's establish a range. Let's say x goes from minus 1 to minus 0.99 to 1. Let's insert a graph. F of x as a function of x. And here's a function. Okay, notice that is a continuous function. It's not smooth because it has a discontinuity of the derivative. Okay, the slope is not continuous at x equals 0, but the function is a single function, it's f of x, so now we can use it as a single function. We can differentiate it, we can integrate it, we can do whatever we want with it because it's now defined as a single function. Okay, we can do that with all kinds of combination of things. We can apply programming blocks for these particular application, or for performing standard programming algorithms. Okay, and finally, MathCAD programming blocks can also return a set of values instead of a single value. So far, we've actually exercised cases in which we return a single value, a in this case, depending on the value of x, a in this case, depending on the value of x. The summation is a depending on the value of n, whichever kind of summation we were trying to do. And the field valve is returning an a depending on the value of a level. We can also use programming blocks to return multiple values, to return a vector of values, for example. So let's say we have a function called cylinder. And this function we provide the radius of the cylinder, the height of the cylinder, this is a solid cylinder, and then the density, rho, as R, Control G, rho in Greek, that is the density of the material of which the cylinder is made of. And we're going to do this with a programming block. And what we're trying to return here is the volume of the cylinder and the mass of the cylinder. Okay? So, let's initialize the volume to 0. Let's initialize the mass to 0. Let's add a line, add a couple lines, and let's say the volume of a cylinder is equal to pi times r squared, that's the area of the base, times the height. And the mass of the cylinder is given by the volume times the density. Okay? Well, the volume is surface area of the base of the cylinder times the height of the cylinder. This is a solid cylinder. And the mass of the cylinder is that volume times the density. What are we going to return? We're going to return now, Control M, a vector of 2 rows and 1 column containing the volume and the mass. So when we implement this function, cylinder, let's say that we have a cylinder with a radius of, 10 centimeters, an h of, 20 centimeters, let's say a radius of 5, a height of 20, and the density, let's say that the cylinder is made of, stainless steel, so it is, I think, somewhere around 7,900 kilograms per meter cube. Here's the answer. Okay. Now I said that the cylinder had 5 meters of radius, 20 meters of height. Okay, it's a big stainless steel cylinder, or concrete. Maybe concrete is a little lighter than 7,900 meters or kilograms per meter cube. And as you can see, let's just modify this result as well. We got 1,570 meter cubes of volume, and the mass is about 12,000 tons, 12,409,290 kilograms. Okay, now let's do this for a hollow cylinder. Let's say we have now a pipe function that depends on the inner radius, or the outer radius, RO, we just call it RO, the thickness of the walls of the pipe, the length of the pipe, and the density of the pipe. And let's try to retrieve again the mass, or the volume and the mass of this pipe. So we apply just simple different mathematical formulas. The volume, let's initialize it to 0. The mass, let's initialize it to 0. And let's say the volume is given by pi times the outer radius square minus the inner radius square, which is RO minus thickness. This is the inner radius, square of that, times the length of the pipe, that is the volume. Just add a couple lines. The mass is again simply volume times the density, rho. And now we're going to return again a vector containing 2 rows with the volume and the mass. So let's say we have a pipe that is 0.025 2.5 centimeters in radius. It has a thickness of, let's say, the walls are about 5 millimeters. So let's say 0.005 the walls, and let's say the length of this pipe, let's say 10 meters of this pipe, and the density, let's say again this is made of cast iron, and let's say it's somewhere around 7,900, and this is equal to this pipe has a volume, the solid part of the pipe, of 0.0071 meter cubed, and it has a radius, or I'm sorry, a mass of 55 kilograms. It's a pipe that has a radius of 2.5 centimeters, or a diameter is 5 centimeters. That's the outside diameter, 5 centimeters. It has a wall thickness of 5 millimeters. It has a length of 10 meters, and it has a density of 7,900 kilograms per meter cubed. Okay, so this is the type of applications that we can do with programming blocks. Obviously, we're just scratching the surface with these. There's a lot more that we can do with just simple 10 statements in the programming block, toolbar, and we can do very sophisticated programs. We can do very advanced iterative routines to calculate many things. But this is just some applications so you can get an idea of what is it that you can do. So this is the end of the presentation with this particular implementation of the programming block, and I'll see you on the next lesson. Thank you very much.